Okay, morning, folks. This time around, we are recapping on normal approximation to binomial distribution. We are saying this is a migration which is done from binomial distribution to normal. We are saying when n becomes large, the binomial distribution choose to mimic the normal distribution. Here and there, because we are moving from discrete to normal distribution. In other ways, we are saying there's a change. Discrete, we are having a numerical whole number format of data values, but with normal distribution, this is continuous. So in order for the two to communicate, we might need a process quite important, which is called continuity correction. So as we deal with these problems, let's please remember the issue of continuity correction. So let's dive into the questions. The first problem we have there is saying, check if x, which is binomially distributed with n equal to 30 and p 0.1 can be approximated by normal distribution. So we discussed earlier that, well, if, let's see, np is greater than or equal to 5 or nq is greater than equal to 5, then we can use the binomial distribution. So let's have a look here to say if we bring in, let's see, let me take my calculator there and say n. I'm given my n there as 30. So it's going to be 30 multiplied by 0.1, which will give me 3. So 3, wow, this is giving me 3. And if I say NQ, that's 30 multiplied by 0.9. So that's 30 multiplied by 0.9, which will take us to 27. So one area matches and the other one fails. So here we can say say if x can be approximated by, then the result there is no, it can't, because this one, the first condition fails. Find the mean and standard deviation of a binomial distribution with all those given values. So we need our calculator again to say from the calculator, um, see what we are given, 120 and 135. So we want NP. So it's 120 times 0.35, which will give us 42. So I can say here a random variable, let me call it Y. Now this time around is normally distributed with 42. I'm sure it's 42. So let's see. I want to pick our icons or the menu. All right, so I want the calculator here. Our calculator is saying 42. So I'm going to say here 42. Then for the other part, which is our variance, it's going to be NPQ. So I need to multiply 42 by 0.65. So I'll bring here 0.65 multiplied by 0.65, which will give us a result of, let's see, 27.3. That's our variance. So our variance is going to be 27.3. Still moving. Oh, here we wanted the mean and standard deviation. So standard deviation is simply root of whatever we have there. Then moving on, we want to approximate binomial distribution using a normal distribution. So here we are simply saying x is a random variable which will be normal with mean. When we multiply these two, it gives us 50, and we multiply it by 2, it gives us a variance of 25, which is actually 5 squared. Moving to the fourth, where we have probability of x less than or equal to 55 for x which is binomially distributed in such a manner. So we can bring another variable y to say this is normal with, let's see, when we bring our calculator there, is going to be 100 times 0.55. So 100 times 0.55 actually gives us, it should be 55 there. 55, um, then a variance of, we'll multiply it by 0.45, 0.45. So let's check, multiplied by 0.45. It will give us a variance of 24.75. 24.75. So this is a variance. We need to remember to put it under the root sign. So on our distribution there, this is the same as probability that y is less than or equal to 55.5. Because we need continuity correction as we go to the upper bound. Then we try and do the sketch so that we can see the region that we are interested in calculating its area. We said the mean there is 55, and here we are interested in probability that x is actually 50 less than 55.5, so it will be slightly in front of 55. So we are interested in all this region to the left. Then we will then move to standardization, and the process we bring phi, and from 55.5 we subtract 55 all over root of 24.75. So when we bring our calculator here, it's going to give us, let's check. We are saying 55.5 minus 55. This gives us this particular result. Then let's bring it on a fraction where we have 0.5 for numerator, and then denominator we can bring root of 24.75. Then we escape again and check the result that we will get. Well, it's 0.1005. 0.1005, 0.1005, and there is a phi there. So this will give us our probability of interest. Let's bring our tables and check what we'll get from this 0.1005. So there is 0.1, and then 0.10 is here. So I can pick my highlighter there to comment. Let's see. So 0.1005, it's going to give us a 1 there. So in essence, I'm going to add a 4 there, which will give us 0.54002, 0.54002, 0.54002, I think 0.5402. That's the probability of interest. So moving on, we have got number 5 there. Use continuity correction to approximate probability. So we are given the distribution again. We are going to say here, this is the same as probability of, let me bring another variable, not z, to say distribution y, where we are saying is greater than or equal to 39.5. But let's check as we bring y, which is normally distributed with a mean. We multiply 80 by 0.45 there, 80 by 0.45, which will give us 36. So I can come here and say there is 36 and a variance of 0.55. So I'll multiply whatever I have there by 0.55, which will give me a variance of 19.8. So I'll come here, I have 19.8. Then from there, I want a sketch to say, but how does my distribution appear? I know my mean is at 36, and I'm interested in greater than or equal to 39.5, which will be this region. Remember, our tables, they only compute probabilities to the left. So what we'll do is, because we want to discard what's in red, we'll subtract it from 1. So this will be equal to 1 minus, then we reverse that this is y less than or equal to 39.5, which will be now 1 minus 5. As we standardize, this is now 39.5 minus 36 all over root of 19.8. And as we do so, we will need our calculator to simplify this, that this is 1 minus phi of, let's check the number that we get as we simplify. It's going to be 39.5 minus 36. So 39.5 minus 36, it gives us 3.5. 3.5. So if I bring my fraction here, 3.5, and then I go to the denominator there is a root of 19.8. Then I escape the root, I escape the equal sign. Let's check in decimal. It's going to be 0.7866. 0.7866. That's the phi that we are interested in. We are saying 1 minus phi of 0.7866. So let's check our tables to say, what do they give us? When I inspect, I want tables. So tables will be giving me, let's check, interested in phi of 0.7866. 7866. So let me move to my 0.78. 0.7 is here. 0, 1, 2, 3, 4, 5, 6, 7, 8. And 66 becomes 67. So it's 0.7866. It becomes 0.7. Let me have a look as we round. This becomes 0.787. So 787, and there is 1, 2, 3, 4, 5, 6, 7. So I'll add 21 there. So in essence, it will give me 0.7843, or 44 rather, when I add that. So that's 0.7844, 0.7844, 0.7844. So finally, I need my calculator now to subtract 0.7844 from 1. So this will be 0.7844 from 1. It gives me a result of, let's check, 0.2156, 0.2156, 0.2156. That's our probability. Now we are on the sixth problem, where we have a region bounded. So this, when we turn to y, is going to be probability that y, as we bring continuity correction, this is 45.5, which is our upper bound, and here is 29.5, which is our lower bound. So because we are migrating, we are going to have y to normal distribution. When I find this product, which is 90 and 0.4, this is going to give me 90 multiplied by 0.4, that's 36. So I'll come here, say I have 36, and my variance of, let's check, 0.4, I'll then multiply by 0.6, and it gives me 21.6 there. 21.6. Then when I do my sketch, because I want to check if there's symmetry. If there's no symmetry, then I know the formula to use. So I'll draw my sketch to say, but this distribution is symmetrical about 36, and I'm interested in 45.5 there and 29.5. So let me try and do a computation to check the differences. In other words, I'm interested in these differences to say, do they bring symmetry? So let's check. I'm going to say 36 minus 29.5, it gives me 6.5. So here is 6.5. Then I try 45, let's see, 45.5 minus 36. Want to check, does it give us, so let's redo this. Is 45.5 subtract 36, gives us 9.5. So there's no symmetry. So rather what we'll do, we are now going to say from our formula, this is going to be phi of 45.5 minus 36 all over root of 21.6 plus phi of 36 minus 29.5 all over root of 21.6, all this subtract 1. So as I simplify, I'm going to check from my tables, what do I get? I saw that here it was 9.5, but I'll just redo the calculation to say, if I say 45.5 minus 36, it gives me 9.5. So I'm going to bring the fraction to say, but 9.5 divided by root of 21.6, and then I escape again and bring the equality. So in decimal, it gives me 2.04. Let me bring again 2.044. Plus phi of, I saw that this was 6.5, so let me try again. It will be 6.5 fraction, and then we need the root of 21.6, and when I escape twice, I look for the solution in decimal form. It gives me 1.399. So let me have 1.399, 1.399, all this minus 1. So I need my tables this time around. I'm going to erase the sketch that I had here so that I can continue with my calculations. Let's see. So as we proceed, this is going to give me from phi of 2.044, phi of 2.044. Let me move 2.044. So 2.0 is here, 2.044. So this is 0, 1, 2, 3. 0, 1, 2, 3, 4. So that's a 4 there, and here it's 1, 2, 3, 4. So it's a 2. So this is going to be 0.9795. 0.9795. So that's 0.9795 plus, when I try phi of 1.399, 1.399. So 1.3 is here, 1.399. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, the last one, and also the last one there. So when I add 7, 7, and 14, it gives me, sure it will be 91. So it's going to be 0.9191. So that's plus 0.9191. Then we subtract 1 from the result. Now we can pick our calculator to do the computation of the probability. This is going to be 0.9795 plus 0.9191. When we check the result, it gives us this. Then we subtract 1 from the result. Our probability is actually, let's check, 0.8986. So our final answer is 0.8986, I think. Let's check. 0.8986. I think that's it. Now, moving to number 7. Explain why large N improves the normal approximation. Our reasoning here says as N increases in size, the binomial tends to follow the normal distribution. I think that's our reasoning there. Then moving on to number 8, find the probability that x is less than 18, where x is binomially distributed with n 50 and p 0.35. So again, what we will do here, we are going to bring continuity correction first to say y will be less than or equal to, it's less than 18.5, which is the upper bound, um, then we are now going to say, uh, well, this one I think is slightly different. When we say, because this is discrete, so when we say x is less than 18, in essence we are saying x is less than or equal to 17. That's the meaning of x less than 18. But then according to our understanding, when we bring y, it will be less than or equal to 17.5. So we are interested in this probability. So let's migrate to the normal distribution, where we are interested in the mean mu. So mean mu, we are going to say 50 multiplied by 0.35, giving us 17.5. So here we have 17.5, and a variance of, we multiply that by 0.65. So multiply by 0.65 gives us 11 and 375 there, 11.375. So here, as we standardize, well, let's first look at the picture of our distribution. This is 17.5, and we are interested in less than or equal to 17.5. In other words, we are interested in this region. So this is basically 0.5. I think that's what we'll get. Then moving to number 9, states 2 advantages of using normal approximation to the binomial distribution. Right, saves lengthy computations and it is highly accurate. Highly accurate for large n. I think basically those are part of the reasons that we can bring. Compare the shape of binomial distribution with normal distribution as n increases. So as n increases, we have a picture like this. This is binomial, was it's symmetrical somewhere coming from the Pascal's triangle. So the comparison tells us that there we are. Now, for large n, this area, it reduces. So the distribution becomes accurate. So as n increases, the approximation becomes accurate. I think that's our reasoning. For now, we can stop here. That was the second part, which is a normal approximation to the binomial distribution. We'll meet again in the next topic, which is going to be permutations and combinations. Thank you.